New Zealand's response?
Yeah, thanks very much, Valerie, and thanks for the organisers for putting together such a fantastic programme and for the opportunity to be here this week. A little bit like James, I have the privilege of standing up here and speaking about some work that's been done by a large number of people, some of whose names will appear at the end of the presentation, but a large number of people, too long to list as well, who deserve thanks. So. Just as an outline of what I'm going to talk about today, I mean, I'll talk a bit about the policy modelling interface and the way that we interacted with government and public health officials in New Zealand throughout the pandemic, and give a bit of a perspective on the contribution that I think modelling made. But I want to talk in a little bit more detail just about two of the sort of modelling tools that we developed and used during the pandemic. The first is a compartment-based model, which we used for sort of a number of different applications, including sort of navigating reopening decisions, as well as operational planning. And then the second one that I'll talk about is a hidden state model that we used for incorporating wastewater data into the sort of situational awareness work, near-term forecasting, and that sort of thing. As many of you will know, New Zealand had an elimination strategy with COVID, which was successful in minimising the spread of the virus until we'd achieved high vaccination rates. Most of the work I'm going to talk about today is work that we did in the period following that elimination phase, when we started to see more widespread community transmission. By that time, we had high vaccine coverage, but very low levels of immunity from prior infection. So yeah, this diagram here is really just illustrating a little bit about the way we worked as a modelling group and the way we interacted with government. So these two boxes at the centre here are sort of the core of that interaction. So we interacted regularly with a cross-government agency group of officials, people from Ministry of Health, people from DPMC, which for the Brits is sort of our equivalent of the Cabinet Office, and also people from Treasury and other government agencies as well. And so we were having regular conversations, regular meetings with this group. They would sort of put questions and tasks to us, and we'd discuss about what the sort of right modelling scenarios to run would be, and then they sort of farmed our results out to the various stakeholders across government. We also interacted quite a bit with the Prime Minister's Chief Science Advisor, and she was fairly pivotal, particularly in the early stages of the pandemic, at sort of shortcutting some of the bureaucracy that exists within government departments and relaying advice directly to decision makers. So overall, I would say the way that modelling results fed into the public health response in New Zealand was more informal than the sense I get from other countries. But yeah, that's just the nature of it, I think. And just a couple of other things to highlight over on the left here. One is that at the start of the pandemic, when we first started doing this work, we set up a rapid peer review panel. So that was a group of multidisciplinary experts, so modellers as well as public health experts, Māori health, sort of people with that social health expertise. And that group, essentially, they would give us some rapid feedback, peer review comments on draft reports and draft modelling descriptions before we would sort of give a final version to government. So that, I think, was quite important in getting some sort of quality control, some peer review on the work we were doing in real time as we were doing it. And the other thing to highlight down here is that we did retain quite a high level of independence from government and the ability to communicate the work we were doing, the results we were getting, and our interpretation of that work directly to the media, directly to the public. That created tension at times. It was a difficult relationship to manage, but overall I think it really was a positive in sort of maintaining transparency of that work, and allowing us to communicate as well as we could how the work we were doing was feeding into that decision-making process. Okay, so yeah, compartment-based model. This was the model that we used for Omicron. Once Omicron became established in the community in New Zealand, which was a little bit later than other places due to the border controls we had, didn't really establish until late January, February of 2022. This model sort of got more and more bits tacked onto it throughout the pandemic, so it ended up like a little bit of a Frankenstein's monster of a model. But the basic structure here is we've got a whole load of different susceptible compartments. The different colours here represent different number of vaccine doses. So the red ones, for example, are people who've had the primary series of vaccines. The yellow ones are people who've had a booster. But also to incorporate the effects of waning immunity, we've got different levels within these categories. So as time goes by, people are moving down through these categories within the same colour, and that's representing lower levels of immunity due to waning. There's age structure in here as well, and then these black ones here are people who have been previously infected, so have high levels of immunity initially from prior infection, but are increasingly susceptible to reinfection as time goes by. And you look at this model and you think, oh my God, this is going to be a nightmare to parameterize. How on earth are we going to work out immunity parameters, different levels of immunity to infection versus severe outcomes for all of these different susceptible compartments? You know, this is going to be an absolute nightmare. What we ended up doing was using this really nice model by David Curry and others at the Kirby Institute in New South Wales, who they essentially developed a model that relates the mean neutralizing antibody titer to the average level of protective immunity with different levels of immunity to infection. So a lower level of immunity to infection, but it's related to immunity to severe outcomes across that curve. So essentially that enabled us to sort of associate each of these susceptible compartments with a representative antibody titer, and then to use this relationship here to map those antibody titers onto immunity parameters for the transmission model. So you get these nice kind of waning curves out of this. So these are sort of different categories of immunity, and you can work out the average level of protection against infection and against severe disease over time. Of course, we had to model waves that occurred due to different Omicron subvariants throughout the pandemic. And the way we did that, we cheated. We didn't try and model multiple variants spreading simultaneously with sort of parameters for cross-immunity. We essentially assumed that there was a single variant, and then on a particular date or over a short window of time, that switched, the resident variant switched to a new variant. The new variant became dominant. And the way we modeled that was essentially we had a sort of short period of accelerated waning. So all of the waning process that's going on continuously in the background, we basically sped that up over a short window of time to represent the immune evasion effects of the new variant. And the way we calibrated the size of that waning, the size of that immune evasion, was by calibrating against these curves here for the share of new infections for different variants, which is coming from the clinical whole genome sequencing data. So from this, we just fitted a sort of simple multinomial model to estimate a growth rate. So this is BA5 in this example taking over. So we've got an estimate of the daily growth advantage of BA5, and we use that estimate to parameterize the immune evasion parameter in the model. So we fitted this model to age stratified data on cases, hospital admissions, and deaths. We had to add in a few ingredients to enable the model to fit sort of 3 or 4 waves as time went by. And the main ones are highlighted down the bottom here. So first of all, we modeled an increase in the contact rate, particularly amongst older age groups, an increase in the contact rate after the peak of that first wave. During that period of time, public health interventions were being progressively relaxed. And I think some of the reactive behaviour that people had to this massive wave for New Zealand, this was the first significant wave with sort of case numbers more than like a couple of hundred. This was the first time that we'd experienced that in the whole pandemic. So I think there was quite a significant component of reactive behavioural change, as well as public health interventions, which then relaxed away. And there was another sort of further relaxation of public health interventions a little bit later on. And then also a couple of sort of new variant effects there, the main one being the BA5, and then a smaller one associated with BQ and CH variants later on in 2022. Okay, so overall these show the fit that we managed to get to the data. We're just fitting this with an ABC type approach. And we're looking at here. So this is the way we eventually settled on sort of, or one of the ways that we communicated the results from these models. So instead of plotting a median here, the median's a bad thing to plot because the median's not a trajectory of the model. We plotted sort of a sample of randomly chosen trajectories and a curve-based 95% confidence band. So that's a band that traps 95% of the accepted trajectories for the model, rather than trying to do pointwise statistics, which sometimes don't capture that uncertainty properly. Yeah, so that was the model. This model got used in various different ways. Apologies for these quality of these screen grabs. I think all of my figures probably fail the figure quality test, so apologies for that. These were just some screen grabs that I grabbed from the dashboard. So we essentially gave model outputs, and a group within the public health agency used those to create a dashboard that district health board planners could interact with and use to sort of get a sense of what the next few months were going to look like in terms of hospital demand. The way we were operating throughout most of this period was we weren't providing sort of near-term forecasts very much. We did a little bit of that later on, but for the most of the pandemic, we were sort of operating more in a what I would call a medium-term projection type landscape. So we would kind of provide these model outputs, and then we'd kind of watch these graphs and see how they go. And if it started deviating too much from the projection, or after sort of 3 or 4 months, we'd update, we'd refit, or if a new variant came along, we'd update the model, and the dashboard would be updated at that time. Of course, the model was used for comparing policy options on a number of different occasions to sort of estimate the effect of relaxing an intervention. In this example here, this is just modelling the effect of relaxing or removing mandatory case isolation. So we've got the sort of status quo as the red one here, and then the purple one, sorry, these aren't labelled, but probably I think the purple one is complete removing of mandatory case isolation, and then the blue and the green are sort of intermediate options with shorter isolation periods. And the last application that I just wanted to highlight here was a retrospective analysis we did of the impact of vaccination. So we had our fitted model that was fitted to that period of time that I showed you in the previous slide. What we did then, once we'd fitted that model, we sort of went back and changed the vaccination rate. So kept everything else the same, but said what would have happened if everything else had stayed the same, but we'd had some different pattern of vaccine coverage. So these graphs here just showing some of the, these are the older age groups, but basically the average vaccine coverage over time, so the average number of doses per person. Of course, the data is split down into which type of dose it was. And the blue curve there is the baseline, so that's what actually happened, and then the other curves are showing different scenarios, and of course we did a scenario with no vaccination at all. So this was really done just to sort of get a ballpark estimate for the benefits of vaccines, the number of deaths that were prevented, the number of hospitalizations that were prevented. So ballpark something like 8 to 10,000 deaths prevented during that 18-month period. Okay, so just moving on to the other model that I wanted to talk about is which we used to do some analysis of the wastewater data. So this here is just showing the green trace here is showing the national estimate for wastewater concentration for SARS-CoV-2. So in New Zealand, we have a pretty comprehensive national monitoring program for SARS-CoV-2 in the wastewater. And this data, as was mentioned earlier on in the workshop, is publicly available. So there are site level, regional level, and national level estimates for it's normalized data. So it's an estimate of genome copies per person per day is the estimate that ESR put out. The other thing that's also in this data set, which is, I think, really valuable, is a breakdown by variant. So you can actually see the sweeps of the different variants taking over, which matches up very well with the clinical genome sequencing data. Okay, so that's the data. We developed a hidden state model to try and incorporate this data into sort of situational awareness and near-term forecasting type models. So the usual sort of thing that many people will be familiar with for reproduction number estimation, we've got a hidden state for the reproduction number, we've got a hidden state for the number of infections, that's the green box, and then we added an additional hidden state, which is the case ascertainment ratio, so the proportion of infections that are being reported as cases. And then two observed states, one is the concentration in the wastewater on day T, and the other one is the number of reported cases on day T. It gives quite a natural way to incorporate the wastewater data in using this type of model, I think. So here we've just got Gaussian random walks for those hidden states, for the reproduction number, case ascertainment rate, standard kind of Poisson renewal equation for new infections, and then for our observed states, it's basically doing the normal sort of thing, a convolution with some distribution of the time from, in this case, the generation, the infection to reporting distribution, and then a similar sort of kernel distribution in there for the time from infection to shedding. So we can fit this model to the data with a bootstrap particle filter, and this is just an example of the results. So we get results out for the reproduction number. Of course, you can do a similar thing without the wastewater data, and you can fit the model just to cases, and you get a similar looking graph out for the reproduction number, but the confidence intervals are a bit wider. So most of the time, the curves match up pretty well, but you're getting a little bit more information by including that wastewater data into the model. And then also, top right there is the relative case ascertainment rate. So in other words, how is the reporting rate changing over time? We can't estimate that as an absolute quantity because there's a sort of undetermined constant of proportionality in there between infections and wastewater shedding, but we can estimate how that changes over time. And if you put some reasonable bounds on what that case ascertainment rate is, you can get different estimates for the absolute case ascertainment rate, but they're all giving a sort of consistent picture for the relative change in that over time. Okay, I think I'm over time, so this is my last slide. So just quickly, a few reflections on the role, the contribution that I think modelling has made. So there are some pitfalls over here. One that I sort of sometimes highlight is that we very often saw model outputs getting confused with model inputs. So I think that's something that's important to sort of try and guard against, being very clear about what is an assumption, what is an input to the model, versus what is an output, what is a prediction, or what is an interpretation that we're drawing. I won't talk through all of these, but just on the positive side, we did have really strong research policy connections, which I think was hugely beneficial in terms of the quality of the work that we did and the impact that it had. I think over time we built very good, high levels of trust and very good understanding amongst our stakeholders of what models could and couldn't do. And I think our models were also a lot better as well from having a good appreciation of the policy landscape and the issues that were important to policymakers. Overall, if I was to summarise the contribution that I think modelling made in one sentence, it would be this second bullet point here. Modelling was just one source of evidence. Though, of course, there were other sources of evidence that were very important, but I do think it meant that decisions were made with a fuller understanding of their likely consequences that would otherwise would have been the case if we hadn't had that modelling. So I'll stop there, and I'm happy to take questions.
A couple of quick questions. Yeah.
Thank you for the nice talk. Regarding wastewater surveillance, what kind of additional data do you think that should be collected to enhance the interpretation?
To enhance the use of the wastewater data? That's a good question. I haven't thought about what additional data might be collected there. I mean, the biggest, or one of the limitations with that data is it is noisy, as you could see even in that national graph. And as you go down to more granular levels, it gets increasingly noisy. I don't know if collecting more data would help with that, or whether that's a sort of just a fundamental limitation of the sampling process.
I understand rainfall, for example.
It does, yeah, and I think that's a contributor to the noise that you can see in that data. They are trying to normalise for that because they're normalising by flow rate. So if there's a big rainfall event and there's stormwater getting into the sewage system, which does happen, that obviously it causes a higher inflow rate into the sewage treatment plant where they're taking the sample. So they're measuring that flow rate and using that to normalise. It's not perfect, but I think that sort of helps reduce some of that impact.
Anybody tried injecting a trace substance into the sewage system?
Yeah, good question. I don't know if they've tried that. I do know they tried to. There's this virus that exists in capsicums, which crops up in the wastewater, and they sort of try to use that as a marker for the amount of human fecal matter that is in a particular sample, and to use that as a way of normalising. They ended up stopping that because I think they were just dividing one noisy time series by another noisy time series, and it didn't really help.
Last one, very quickly.
Do you think we need better knowledge about the infection to shedding distribution? Because I assume that you are using human shedding, but from the respiratory tract, but not from the GI tract.
That's right. Yeah. Yes. So yeah, I think that would definitely help, and that would be really useful information to have. I mean, the other big unknown and the big limitation, I think, with using the wastewater data is this unknown relationship between number of infections and an amount of viral DNA that's coming out. So, and how that's impacted by things like immunity, different sources of hybrid immunity, different variants, could be causing that relationship to change over time. So if we can somehow get some data that helps pin that relationship down and estimate how it's changing, I think that would help benchmark models like this and other approaches to using wastewater data a bit more accurately.
Thank you. So thank you very much again to Mike. Thank you to all the speakers, perhaps, for this morning.